Alrighty guys, so we're going to talk about how to read the stoichiometry roadmap correctly. Note that as you look over the stoichiometry roadmap, you probably are noticing that it looks kind of like roads and streets. That's actually part of the design, but the symbols on the stoichiometry roadmap are the most important parts, not so much its shape. The two most important things on the stoichiometry roadmap include the boxes and the double-ended arrows. One second. Okay, so first off, guys, the boxes actually represent locations in terms of keeping it like a map. And the double-ended arrows represent kind of streets if you're still keeping it to the maps. Note that the locations are actually your knowns and unknowns that you can have. Ergo, they're like starting and stopping locations. The double-ended arrows, being like streets, mean that these are the relationships that you multiply by to get from your knowns to your unknowns. There's also some additional information that is useful in reading the stoichiometry roadmap. In addition to the double-ended arrows telling you how many relationships are in between points or between your known and unknown, it also tells you the name of the relationship, and it'll give you the fraction on the bottom part, or the bottom of the double-ended arrow. Real quick example, if you started with something like a known of, let's say, 200 grams of H2O, and an unknown of liters of O2, and your balanced equation was 2H2O, 2H2 plus O2, you would go ahead and you would translate your known and unknown into map speak by looking at the unit, write it out. G stands for grams. In this second example for your unknown, L stands for liters. And then for the formulas, you would designate them a letter. Because known is first, really, it's the first thing we look at, we're going to call this first formula of H2O A. That means that every time we refer to an A on the map, we're talking about the formula H2O. Not the coefficient, but, the formula H2O. When we look at our unknown, we have liters O2. This formula, O2, is not the same as our A substance because it has a different chemical formula, meaning that this is going to have to be designated a second letter. This letter will be B. It's the only other letter on the map. Taking a look at the map, as you can see, we were starting at grams of A, according to our known, and we're going to liters of B. So grams of A to liters of B. In between these two locations, there's 1, 2, 3 double-ended arrows. That means that there's 1, 2, 3 relationships. That stoichiometry roadmap also tells us the type of relationship, so we'll refer back to that and we'll write it down. Okay, the first relationship being molar mass. You should write that down next to the 1. The second relationship being mole ratio. And the final relationship being STP gas. Can you guys see that? There we go, STP gas. The fractions underneath will be written in a second. Note, I'm going to copy them exactly down like they are written, but in fraction, or sorry, actually, no, not even going to be in fraction form yet. We'll wait till calculation for that. Okay, so as you can see, I've labeled my relationships, molar mass, mole ratio, STP gas. What comes after it is the fraction. We're going to put the fraction that was on the bottom of the arrow, double-ended arrows, next to it. I actually have a stoichiometry roadmap on hand right here that I'm going to refer to. Next, underneath molar mass was number grams A equal 1 mole A. Under mole ratio, number mole A equal number mole B. And finally, for STP gas, just so you can see, note it says 1 mole of B equals 22.4 liters. Okay. This information is very, very important. We do need to flesh it out a little bit, though, because this is a general set of information for any calculation. For each of our A's, we need to replace that with the actual formula. Remember, the formula for A was H2O. For B, we need to find out what B is. B was O2. So every B needs to be replaced with the actual formula, which was O2. Now we have all of our formulas in the correct spots for our relationships. Next, every number sign needs to be replaced with the correct number. For molar mass, we find this number sign with the periodic table. So we need to find the masses on the periodic table for hydrogen. It's 1.008. So molar mass step, hydrogen. There's 2 of them, so we're going to take that 1.008 and multiply it by 2. Then oxygen is in this formula. That is, let's look at it, 15.999. We're going to round that to 16.00. And technically I could round it up to another 0 even. Calculate and add the 2 sums. Okay, we'll just do this calculator. Times 2. Nope, did that wrong. 1.008 times 2 plus 16. Molar mass is 18.016, meaning that that's what we're replacing the number sign with here. Down here, we get the mole ratios for A and B, or for H2O and B and O2. Remember, this comes from the balanced equation, so we go up to the balanced equation. We have a 2 in front of H2O, so we replace that number with a 2. In front of the O2, there is no number, so it's an implied 1. Place with 1. This is our relationships, and now we plug it into our calculation. Alrighty, guys, I hope this has been helpful. You will see another video working out question 1A and 1B for the Amazing Mole worksheet.